So now, what I want to do today, just to sort of start off from what I did last time. So let me just quickly recall what we were doing last time. So I had done two critical transformation random variables. So I had taken x and y independent random variables. With joint PDF. They're not joint PDF, they're independent. So with PDF f sub x and f sub y respectively. So they're two continuous random variables. Then I discussed two aspects of it. One is this is called what I call the sum. Here I said that if z is equal to x plus y, then the density of z is given by, so here I put this in red so it's sort of clear what this red was about, was the kind of the convolution of x and y that's given by minus infinity f sub x at the point x and f sub y at the point z minus x dx. This is one thing we discussed and derived last time. Yeah. So from this, I had shown you one important fact that I had shown you an example where I said that. So I done an example where I said you take x equal to x is exponential lambda, y also exponential lambda, then z, the density of z was given by z e to the minus, let me just get that formula, gamma formula correctly, I always make a mistake. So it's lambda squared z e to the minus lambda z, z again. Let's erase it back again. Lambda squared, again, lambda squared z e to the minus lambda z, when z is not negative and 0 otherwise. This is the thing we derived, and I said that this was sort of an extension of what's called z is what's called gamma 2 lambda, and in general, let's say w is gamma n lambda if the density of gamma w is given by so we'd have lambda to the power n minus 1 by n minus 1 factorial. And then x power n minus 1, sorry, not x, you know, w power n minus 1 e to the minus lambda w. This is for w non-negative and 0 otherwise. So this is called gamma random variable. And I'd also suggested that this could be done inductively. We could show that w is the same as x1 plus x2 plus xn, where each xi was exponential. This is an exercise I actually given by induction questions. So the next thing we did was I stated this thing. I don't know if I did it completely. So I said next was quotient. Here I said, excuse me. Here I said that if z is equal to x by y, the density of z is going to be given by not the convolution, but a little bit different formula. So let me just derive this. So here I said if z is equal to x by y, then the density of z, again, let me use the red part, is going to be given by the integral from infinity modulus of y f sub x at zy times f sub y at the point y dy. This is how we derive this thing. Again, so z has PDF given by this thing. So both these things have z is equal to z. Z is also continuous, and z has PDF given. And if you go up here, it's also here z has z equal to x plus y. Let me just erase this a little bit. So here, so erase this down a little bit. Here, what I should have said exactly is z is equal to x plus y has a PDF given by. So this is where we were last time. I'll just summarize this a little bit so you can see the whole page. Very good. So now I just want to do a one more example. So gamma came out naturally as a sum of exponentials. There are two interesting and important random variable in statistics, which I'd like to illustrate by doing a couple of examples. So here now, if I take if I do the following, so I do an example. This example, let's call it as example 5.5.9. Here, let's say I take x is normal with mean 0 and variance sigma squared. Let's take it that way. Then maybe I'll take variance 1 just to make computation easier. Variance 1, and I take y also to be again normal 0. Okay? Y also to be normal 0. Independent random variables. Right? Another variable. So then I take z equal to x by y. So from the above description right here, if I want to compute the density of z, I need to just understand how f sub x zy times f sub y behaves, and then integrate out with mod y to get the answer. Let's just do that quickly. So what happens first we do is that f sub z at the point z is equal to f sub x at the point zy times f sub y at the point y. Right? This is what we got for any z in R and any y in R. Let's just define this. Let's start with this. So this we know f is normal, and x is normal. So this is going to be e to the minus. This is z squared, y squared by 2, and y squared by 2 is normal 0, 1 by root 2 pi, and this person here is going to be e to the minus y squared by 2 over root 2. So there's no sort of ambiguity there. That's easy to think. And then now you just have to be a little careful to write this down as this function is going to be what? E to the minus. So this is as 1 plus z squared. That's a constant term. I'll leave it as it is by 2 y squared by 2 pi. That's what f sub z is. And then, so it's not f sub z. I'm sorry, I made a mistake. This is just a computation. I'm sorry about this. This is just a computation. This is not f sub z is going to be integral of this. So f sub x, let me move across. So f sub x times z sub y is going to be equal to this. Maybe I can move this up. This, and this is variance. Now we know from the above formula that f sub z of z is integral of this form, right? Let's try. So now f sub z of little z is going to be minus infinity mod y So yeah, I think that is the convention of z in red. So z in red mod y times this function. Right? So e to the minus, e to the minus this by 2 pi 1 plus z squared, right? And then you have y squared by 2, and you have a d1. This is what this is. So now it's a calculus exercise. So it's an exercise in calculus to show the following: that this is a even function on both sides, and the integral is finite. That one has to check. And once you do that, this is the same as 0 to infinity, and it's twice of this. So it's 1 over pi comes out, and then you have y times e to the minus of this percentage. So 1 plus z squared by 2 y squared d1. So this is the calculus exercise. Now this you have a y and a u squared, so you do a u equal to y squared as a change of variable, right? Substitution. So once you do that, so we just do y squared, and you put y squared in blue. This will give you that this is equal to what will happen. It's just going to be 1 over pi. So 1 over pi, and then so maybe I don't want to do this. I want to do something a little bit more general than this. Let's say u is equal to I do 1 plus z squared times 1 plus z squared times y squared. That will be the best one. Square times y. So I just get this is the same as pi into 1 by 1 plus z squared on the outside, and inside I just get integral 0 to infinity e to the minus t over 2. E to the minus t dt. So maybe to make life simple, I just divide this whole thing by 2 as well. Do I need to? No, I don't have to do that. Yeah, if I do this, I need this to do that. Very nice. Right. So I do substitution, then I get this. But this we know is just the same as we do capital exercise, the same as just 1 over pi into 1 plus x. The ratio of two normals is quotient. So this is quotient 1. So z is just quotient. Okay, very good. So that sort of sums up my discussion on transformation random variables. We'll do a quick recap of this thing, and then so I'll give you two examples in the homework of two important random variables that come out as transformations. So which are one is beta and one is f. So that I will give it in the homework, and then you can compute it and check the answers. Okay, very nice. Okay, so now let me start off on two things. So now let me just recap a little bit from discrete random variables. These the average played a crucial role in discrete random variables, and so did the expectation. So let me just sort of revisit those concepts. So so this is 6.1. So I want to revisit concepts of expectation and variance for continuous random variables. So here the again I'll start off with x being a continuous random variable with PDF given by f sub x. So x is a continuous random variable. PDF given by, let's say, f sub x. Then its expected value of x. In the discrete case, we know we would just sum up xi with all the probability xi equal to x. In the continuous case, we would integrate. So we would integrate out x given by infinity x times f sub x. Okay, that's the definition of expectation. So this is what's outlined in definition. This is definition 6.11. So e of x is just the integral of x. So again, now when you state an integral like this, if you were to go back to your calculus or analysis days and see that this is only defined if the integral converges absolutely. So if the integral converges, so it's provided that the integral converges absolutely. Otherwise, this is not well defined. So in this case, you say x has finite expectation. And so this is sort of in quotation. Otherwise, you have to sort of go in the uncertain world. So if the integral diverges, then you just say that random variable is infinite expectation. We say x has infinite expectation. Diverges. This diverges to here. Let me put it in red. Diverges to plus minus infinite. That's when you say that expectation. So diverges to plus minus infinity. You say it has infinite expectation. Otherwise, if the integral just diverges, either not to plus minus infinity, but doesn't converge, then you say that. So here, not to plus minus infinity, then you say that then we say x does not have expectation. Or maybe a better way of saying it as e of x is undefined. E of x is undefined. Let's say e of x. This is something that one has to do integrally in that sense. So same way like we did in sum, when you had a countable sum here. So let me just do a couple of examples. So let's do an example. 6.1.2. If x has a uniform AB, when AB, let's say A is less than B, two numbers in a real line, then let's do what E of x looks like. So what does E of x look like? So f sub x of x, is going to be equal to 1 over the length of the interval with B minus A, when x is in A, B, and 0 other one. Then E of x, what's E of x going to be? E of x is just integral into infinity x f sub x of x dx, right? That's what the definition is. Now the density is positive only in AB, So it's going to be equal to a to b x, and the density is 1 over b minus a dx, and that's just going to be just 1 over b minus a. And this, I don't know how you do calculus, but I'll do it like this: x squared by 2 a to b, and if you rewrite it, that's just going to be just b plus a. Right? So the mean of the uniform is like, or the expected value uniform is b. So in probability, you interchange expected value. If you recall how we did it for discrete case, it's the same as interchange the value or interchange the name of expected value and the mean as sort of interchangeably used. So just notation. So you call E of x as expected value or E of x as the mean, it's just sort of the same. So let's do another very important distribution in probability, which I will not motivate, but how it comes about, but it's sort of used in a lot of applications like insurance and all. So let me write this down. I'll write the density down a priori in artificial manner, but it comes from applications. It's called the Pareto distribution. So you say x is a Pareto alpha if its density function is given by alpha by x to the alpha plus 1, 1 less than equal to x less than infinity, and 0 otherwise. Right. So now here, let's just graph the density a bit. So here, I don't know if you notice it. So, so let me just draw this in black, the axis in blue. So I'll tell you why this is sort of important. So one thing to understand is this example is the following, that this is what, this is 0 to here, and then it sort of decays, right? Decays like this. It starts at alpha, let's say it sort of goes up to infinity, right? So it goes up to infinity. So here it sort of it starts at 1 to 1. To 1, and at 1 this point is let's say alpha right here, and then it comes down, right? So that's how the function looks like. That's how f looks like. F sub x. So now they just have to sort of think a little bit, and then suppose I have let's say y is exponential lambda, right? Or exponential 1, let's say. Then we know f sub y at y is what, e to the minus y being equal to 0, and 0 if otherwise, right? This is what exponential look like. So exponential also will mirror this on the negative side. It will be a 0 here, and here it will start at 1. Let's say alpha is less than 1, and then it'll come down, but then it'll quickly cross this thing at some point in time, and then decay exponentially. So in some sense, the thing I want to point out is that the probability of y bigger than y, right? That's the same as y to infinity e to the minus, let's say y bigger than, let's call it as t. Maybe t is maybe, let's say y is t is t to infinity e to the minus y dy. Let's say t is positive. This, and that's going to be the same as just e to the minus t. Right? That's how it's going to be. That's the output of this. Similarly, if you go and do this other expression, probability that x is bigger than t. X is bigger than t. That's t to infinity. Again, I will put t in green. T to infinity. And here I have, let's say t is bigger than 1. since both calculations are valid. So t bigger than 1 is going to be alpha by, sorry, not in green, in black, alpha by x to the alpha plus 1 dx, and that, if you just do a simple calculation, is just 1 over t to the alpha. That's all. Very nice. So let me just make it a little bit smaller so you can see what on screen. So so one thing is that, one thing I don't know if you notice immediately that so let's put this as we just illustrate the difference. Let me write this in red. Is e0 minus t, and let me write this in black so understand the difference. This is t to the alpha. So one thing you notice immediately is that the chance that x is bigger than t decays polynomially, whereas y bigger than t decays exponentially. So this Pareto is an important distribution when you want to model events where the tail probabilities are decaying polynomially, not exponential. So just to sort of make that precise, I'll just write a couple of words. So here, here the way you identify this is that you say that the tail is decaying exponentially, because it's like exponential functions, like. And here the tail is decaying polynomially. So here the idea is that that the tail is a little bit fatter. So that is, the black is above the red line. The tail probability is fatter. So these are called heavy tail anomalies. These are called heavy tail, and these are called light tail. So anything with I mean, light tail is not used, only heavy tail is used, but I just call it light tail. So what was I doing? I was just discussing what Pareto was. Let's compute the expression of Pareto. So let's say x is Pareto alpha, then E of x, what's E of x? E of x is minus infinity x times f sub x and x dx. That's the distribution of Pareto. What's that going to be? That's going to be 1 to infinity, right? Alpha x to the alpha plus alpha minus alpha dx. That's the dent. That's what. So alpha comes out. So then let's just work it out. So this, the way you would do it is, you would say is limit as m to infinity, right? 1 to m x to the minus alpha dx. Now this guy is going to be what? It's going to be alpha times limit as m goes to infinity. This person right here is just going to be, if you do the calculation correctly, is just m to the minus alpha plus 1 by minus alpha plus 1. And then minus 1. Yeah, that's how it's going. By minus alpha plus 1. That's the calculation. So now, if you just think a little bit, if my alpha is less than 1, like I said, so I want to go back and define a Pareto. So 0 less than alpha less than 1, then this quantity is infinity. Right? When 0 is less than alpha less than 1. So in some sense, if the decay is t to the alpha and the alpha is less than 1, then the mean is infinite. The expression is infinite. This is one example where you see that the mean is infinite. This is something I'd like to sort of illustrate. Right? So let me just do another interesting thing, show you a small thing. Let's see if that comes out correctly for me in my gymnastics. So here I had this idea that the Pareto was of this form. Then let me go back here. So we ended up the discussion with the transformation to be Cauchy, right? So if you stare at Cauchy for a while, you can actually show that Cauchy's mean is not defined. The expression will not converge. One can also check that. So let me just make a remark that so if x is just a remark. one could check if x is Cauchy 1, right, like we did before, then we know that E of x is integral minus infinity x times 1 by 1 plus x squared times pi dx, and one can check that this integral does not have diverges. Integral diverges to neither plus infinity or minus infinity, because it's an odd function, so you think it's converging to 0, but it's not. It's just it's going up and down. So in this case, E of x is not defined. So I'll put this in quotes, E of x is not defined. So for Cauchy random variable, the mean is not defined. So similarly, so there's interesting ideas in probability about heavy tails and how the mean is infinite. Cauchy is a model where the mean is not defined properly. Let me do another extension. I'll stop this session. So one is that let's do a. So I call it. Maybe I should just call it as a theorem whose proof I will not do. See, suppose I have x. Sorry, let me go back to black. Suppose I have x is a random variable with PDF f sub x. Right? So that's a. So again, by this I just immediately mean it's a piecewise continuous function from real line to real line with integral one, non-negative integral. So now this is one thing I'd like to sort of see. We have done this idea before. We said that if g is a function from the real line to the real line, and I had z is equal to g of x, so we prescribed the way in which we could find the distribution of z. So then you could go and find the distribution of z and then try to find its mean from distribution. But this interesting formula exists. E of z is given by the integral from minus infinity to infinity g of x f sub x and x dx. So you don't have to go and find the distribution of z, the whole thing. Just do this directly, g of x, just like we did for the discrete case. And b, let's say y is another continuous random variable. Random variable. And let's say x and y have a joint density f of x comma y, right? Joint density f. Then you take, of course, you take an h from R2 to R2, R2 to R, and let's say z is h of x comma y, so it's a function of two variables. Then E of z is going to be a nice well-defined random variable. You could go and find the distribution of z and then find its mean. But if you just want to find its mean, then it's just given by the formula h of x comma y. Then you have a double integral h of x comma y, f of x comma y, dx. So there are two important identities that we think. So let me just comment on two things. So the proof of this is a analysis exercise. I'll omit for this. I'll omit the proof for this course. It's just it's a bunch of remarks I'd like to say is that just the usefulness of this is the following: is that you don't need to find distribution of z in A and B to compute the mean. Compute. That's all. That's the punchline of this. So let me just recap the discussion. So one was that if you want the mean of E of x is given by this, in some sense, then we did one example of uniform, which is b plus a by 2. Then another one was Pareto, which was like I discussed Pareto as an example in application probability. When you know the tail probabilities are not very small, not exponentially small. They're used in finance and insurance a lot. The data is not normal, or not exponentially decaying. Then once I did Pareto, I showed you that I discussed briefly that X is Cauchy means that it may not have an expectation. And if you want to compute functions random variable only its mean, then you just have to integrate the function with the density function, that is g of x, f of x, f of x. And similarly, the case in two variables, that is h of x, y, Okay, I think this is a good point to stop, and I'll come back and discuss more about expectations.